Hello, ELT132. This is Roger Young, and this video is on the Universal Shift Register. So this is the final shift register we're going to be talking about in the class, all right? So if you look at this shift register, it basically has four modes of operation. And you can tell down here from the legend, right? So one mode of operation is a hold state. That's basically where if you clock it, the output will be fed right back to the input and it won't change the value. So that would hold the value right where it is. You're going to also have a shift right and a shift left. Those were previously discussed in the earlier video. And finally, we have a load. This is the last one. The one type of shift that we did not discuss, in other words, have a schematic, is the parallel load. And that's what this does right here, okay? So why don't we just go through it. In this video, again, you have 4 D flip-flops, right? Pretty standard, that from what we've seen before. And now, the prior video, we had 2 AND gates feeding an OR gate, right? Well, in this case, we have 4 AND gates feeding each OR gate. Now, just think about it. We have 4 choices or 4 types of shift registers we can work on here. And how many do we have here? Well, we have a hold, we have a shift right, shift left, and a parallel load. So we have 4 types, right? So it makes sense. So depending which one of these gates is going to be enabled is going to determine what type of shift is going to take place. Now, to determine that, you can easily see that you have 2 control inputs, S1 and S0. Now think about it. If you have, let's just talk about this. This is S0 and suppose this is S1, right? So what can you have here? And let's say this here output Y. You can have it be what? You can have it be 0, 0, 1, 0, 0, 1, or 1, 1. Right? Those are the 4 possibilities. Hence, you have an AND gate for each one. And if you look down here, there's your legend. It matches it just right. So just as it's written down here. So if we go through this, let's just start with one set of gates. Let's just look at this one here on the left. And if we're looking at the leftmost gate right here, right, leftmost gate right here, boom, boom, boom. Now, for that to be active, you notice previously we just had one line that came in. It was a 2-input AND gate, and only the single line had to be high to enable the gate, right? Well, in this case, we have 2 coming in, don't we? Because they're 3-input AND gates. So if you come up here, we just follow these lines all the way up. Here they are, right? They terminate here. So in this case, for this one on the left, if you notice, S1 has to be low, and S0 has to be high. It's this case right here, isn't it? And notice what it says, shift right. What do we have feeding that particular gate? It's called RSI, right shift in. So your data is going to come right through here and down. It's going to come through this gate, through your OR gate, into your input. And what's going to happen? Well, the output here is obviously going to go up here, come down to this gate, right? Right on through and into this flip-flop. The output of this flip-flop, the same thing's going to happen. Follow it all the way down, and then this one is going to come right up here, follow this all the way down, and there you go. And then finally, your Q output is shifted into bit land, right? So that's the first case. Let's do the second case. What about this one? I'm going to put double dots there. Let's look at that one. Here we are. So this one. Well, first off, what's the feeder? In this case, it's P3, right? How about this one? In this case, it's P2. In this case, it's it's P1, right? And on this case right here, come over here, it's P0, isn't it? So this P stands for parallel. It's a parallel shift in, right? Now if you follow these up, this one for example, S0, it goes right to S0, right? So S0 would have to be high, and this one, it goes right to S1, right? So S0 and S1 both have to be high to enable this gate. Well, what do we have here? If they're both 1, 1, we're looking at this right here, aren't we? We're looking at that one. So when both S0 and S1 are high, with one clock pulse, you're going to load each of these flip-flops based on the value at the inputs from this parallel interface, right? And then with the next clock pulse, those are all going to be shifted out, and you're going to have new values coming in, right? So there's your shift, there's your parallel. How about this one? Let's just do this one, make it a big dot. So we're looking at the third gate, right? So if you look at this one, where's the data coming in for this one? It's coming in. This one, these two are control inputs. We'll see that in a minute. It's coming here, come all the way down over here. It's coming from the output of the flip-flop to the right of it, which tells me this is going to be a shift left, because what was here is going to end up coming in here. Well, let's see what it's going to take to enable that gate. Both of these have to be high, so that means S0 has to be a 0 to make it a 1, right? So S0 has to be 0, and this one also has to be a 0. Is that right? Wait a minute. I'm sorry. So this one has to be, S1 has to be a 0. I'm looking at the wrong one. That's my fault. I'm sorry. We're on this one right here. So S0 would be low, and S1 would be high. S0 would be low, S1 would be high. They were on this one right here. That's a shift left. And that's exactly what we saw, right? Because the output here is going to come over right through this gate back to the input, right? And for this one, it's going to come up, come over, come down, right through this gate. So what you have here is a shift left. Obviously, here's your left shift in, right? That's going to come this way. That's the feeder, right? Just like right shift in was the feeder for the right shift, the left shift in is the feeder for the left shift. Finally, we have one more item, and that is this one. That's the hold. And that obviously is this one right here, the one on the right, okay? So if you look at the one on the right, both control inputs go to the not states of their output. So it's going to be 0, 0 is going to equal 1, 1. So you can tell we're right at this state, right? So if S1 is 0, that means S1 not is a 1, which would make this line high. And S0, I'm sorry, that was S1. In S0, if this is low, that's going to make this line high, which would come in and make this input high. So both of these would be high, which means the chip would be enabled, right? And if you look at the output of this chip goes up, comes right down, and feeds right back to the input. So every time you clock it, it's just going to outload, it's going to reload what it had originally. So that's called the hold. It's never going to change. What is the output becomes the input. So if there was a 1 here, you're going to feed a 1 on every clock pulse, and it's never going to change. If Q was a 0 and you feed it and you clock it, it's going to stay 0. It's never going to change. Remember that Q follows D. That's the rule for a D flip-flop. Well, this is known as a universal shift register, and that was the discussion of how it works. I hope this has been helpful to you, and thanks for watching.